Does that expression strike any bells for anyone as to what it is? What is it? E to the x. Yeah, it should be a function. So there's like a power series representation for e to the x. And you can do things with this. This object, right? So even if you don't can't figure out how to make sense of what an exponential should mean with an irrational in the exponent, that's fine. Use this to make sense of it. Everything here just makes sense. It's raising two integer powers. You just have to add up infinitely many. But that means you better be worried about some stuff. You're taking a limit, right? That's what a series means. But not just a limit of a sequence of numbers. For each different x, you have a sequence. This is like a sequence of functions. And each of the functions you're studying, you can continuous functions. Even differentiable, anything you want to say about polynomials. We haven't talked about derivatives, but a sequence of differentiable functions. What can you say about the limit of such a thing? And that's important because, as you see in Taylor's theorem is an important, powerful theorem. It lets you approximate interesting problems. Many people have taken well, everyone's taken a little bit of differential equations because you took Calc 2 and you do some differential equations there. Anyone take any of the devoted DiffEq classes that are here? So in that class, do you hit the idea of writing down power series representations for solutions? In that class, do you worry about whether the power series you find actually converges? You should at least a little bit. Otherwise, you may have written down a solution that just doesn't exist anyway. But that's a powerful tool. You can write down new functions if you can write down a power series. So let's start building up the framework you need to talk about that. Let's talk about sequences of functions and what their limits mean. Fair enough? So, and hopefully no one here is going to struggle like a Calc 2 student does sometimes with the difference between a series and a sequence. I think we're past that. The sequence of partial sums is the thing you're going to stick it in there. Anyway, whatever. So what is a sequence of functions? It's a sequence worth of functions. So something like that is a sequence of functions. There is a sequence of functions. For each different value of n, you get a different function. Hell, they could be the same function. You're allowed to have constant sequences. Here's maybe a more formal definition. Let U be a subset of R. For every natural number n, let f sub n from U to R be a function on U. Then that collection of things, f sub n, is a sequence of functions defined on U. That make sense? On the other hand, a sequence of functions, that looks like they're just two independent variables, right? There's an x and there's an n. And then if you have some formula, there will be some x's and n's in it. So a sequence of functions is a function from U across the natural numbers to the real numbers. And there's a rule translating between these two things. Those all seem sensible enough? And there's nothing deep here. That's a definition. So what's the thing you do if you're an analyst with a sequence? You take its limit. I have these sequences. The whole thing I want to think about is what do they approximate? What's the limiting object? So let's think about what the limit of a sequence of functions should mean. And depending on exactly what you want to do, there are dozens of different definitions of what it should mean for a sequence to converge. I think I'm going to give 2 of them. In fact, I know I'm going to give 2 of them because I planned out the notes from here. And I won't get distracted and talk about the other ones. So here's the most obvious definition of what it should mean for a sequence to converge. A function f from U to R is a pointwise limit of a sequence of functions, fn, also functions from U to R, if for every x in U, there's a sequence of numbers, f sub n of x. So fix a single input value, and now let n go to infinity, if that sequence of numbers converges to f of x. That seems like a reasonable enough definition? Yeah, maybe we'll just formalize that a little bit. I'll underline this bit in red. So let's quantify that out. Fully quantified definition of the limit of a function. We say a sequence of functions f sub n from u to r converges pointwise to a function f from u to r if, for all x in u, expand out the bit in red. What does it mean for a sequence of numbers to converge to a number? What's that mean? I'll give you that much for free. Well, so Thanksgiving break wasn't that long, but let's try to rebuild it. So what should it mean for a sequence to converge to a number? It just means these numbers can get as close as you want to the limiting number. So you should be able to arrange that. And you should be able to arrange that by taking the number little n to be really big. So there should be some threshold value, which depends on the choice of epsilon. The smaller epsilon is, the bigger big N should have to be, such that as soon as little n is past this threshold value, you get that. Now that it's written, it looks familiar. So what does it mean for this sequence of numbers to converge to that limit? It means for all epsilon bigger than 0, there exists a big N such that for all little n bigger than this big N, the difference between this sequence of numbers, f sub n of x, minus the limiting number, f of x, is less than epsilon. And now take a look at that definition. Imagine you are asked to prove that some explicit sequence of functions converges pointwise to a limiting number. You'd start by saying, consider any x in u, consider any epsilon bigger than 0, then you'd have to come up with a choice of big N. What things could that big N depend on? Yeah.
Epsilon and x.
Epsilon and x. So maybe here's the remark. Different x's can get different big N's. So if you like, the rate at which the function converges to this limit will depend on where you're checking the limit. And as we saw when we talked about uniform continuity, you can get some bad behavior out of just a definition where you're allowed to do different things at different input values. So there's an obvious variant on this definition. And I'll write it on the next page. So a sequence of functions is called uniformly convergent to some uniform limit f. If you change this definition so that the choice of big N is not allowed to depend on x, how would you change this definition to prohibit big N from depending on x?
Move the for all x and u over to the for all n greater than n.
Yeah, if you move the for all x to here or there, it doesn't matter what order you put universal quantifiers in. And it doesn't matter what order you put existential quantifiers in, but it matters if you swap the order of existentials and universals. Yeah, just move that to after there exists a big N. With that in mind, here it is. Let f sub n be a sequence of functions, another function f from u to r, or another function f from u to, oh no, that's grammatically correct. We say that f is the uniform limit of f sub n if for all epsilon there is a big N, so that for all little n bigger than big N, for all n in the natural numbers, if little n is bigger than big N, then for all x in u, absolute value of f sub n of x minus f of x is less than epsilon. Oh, yeah. Yeah, all I wrote is the thing that you knew I was going to write. But yeah, better to be on screen. So the whole difference here is now big N depends only on epsilon. And there's a good reason to do this. Uniform limits inherit behavior that pointwise limits don't. And in order to see an example of this, and also to see an example of actually using these, like proving some toy example with these statements, here is a proposition. For every natural number n, I will define f sub n from 0, 1 to r by the rule f sub n of x equals x to the n. That give me a sequence of functions? No. I have a different function for each different choice of little n. Let's set f of x to be the function that is 0 when x is in between 0 and 1 excluding 1, and is just 1 when x equals 1. I claim that the sequence of functions fn converges pointwise to this function f on the whole of the closed interval. If you take any c smaller than 1, then the convergence is uniform, at least between 0 and c. And if you look over the whole closed interval from 0 to 1, this convergence is not uniform. So there's like some statements to prove. And maybe before we, well, no, I think we should prove it first and then like revisit it, and then there'll be some observations I want to make. Let's prove it. So let's start with the first claim first. Let's start with this pointwise convergence claim. So let's define f sub n from 0, 1 to r by the rule f sub n of x equals x to the n. Let's let f of x be this function that I'm alleging is the limit. You know what, before we even do that, like, let's visualize. I know that like, this is maybe the first time I've pulled up a Desmos interactive in this class. But here's the sequence of functions for like some different choices of n ranging from like 1 to 100. Maybe we'll start at 1. Start at 0 even. As n grows, does that sequence of functions seem like it's getting close to the function that's just 0 on the whole interval? Yeah, well, except at 1, right? At 1, x 1 to the n is always 1. In fact, maybe 100 is not like big enough. There, now I'll just keep going. No, you can't see it now. Yeah, okay. Okay, not a good visual anymore. But it's not a good visual because like it's basically achieving the limit. So, it sure seems like this convergence is happening. Let's try to come up with a proof, and let's think about what we need to prove. So maybe we'll like go to the board, figure out the want to show, and then we'll come down here and try to like come up with a proof. So I want to show if f sub n of x is x to the n, and f of x is I want to prove that. So what is it that you want to prove if that's what you want to show? There are like two versions of it. So you want to show for all x in the domain, so I guess that means, yeah. There's what I need to prove. Let's just try to stare at this for a little bit. Right, like, there's obviously going to be some case-wise stuff because there's a case-wise function involved. So maybe we'll deal with like the weird case first, when x equals 1. So when x equals 1, why should this happen?
110 power is
120 power. It's a constant sequence. Oh, cool. Let's plug that in. So let's define f sub n at the appropriate rule. So with pointwise convergence, I can consider any x in 0, 1. I need to show that f sub n of x converges to f of x. That's in terms of sequences of numbers. Let's consider the case x equals 1. In that case, as you just said, what is f sub n of x equal to? Just 1. 1 to the n is 1. Oh, that's a constant sequence. Does not converge, it converges. Where does that constant sequence converge? Is that exactly where I needed to converge? All right. Nice. Could you do something similar with x equals 0? Yeah. So I don't think that's so important. I think it will be important in the... Let's come up with the rest of the proof and decide if the second half of the proof applies when x equals 0. Even if whether it does or doesn't matter. I think that similarly we can do the same thing when x equals 0 is good enough. So I mean, I don't know. Does the exact same set of odds apply when x equals 0? Yeah. 0 to the n is 0, so it's fine. So let's assume that x is strictly between 0 and 1. Let's consider any epsilon bigger than 0. We'll need to come up with a choice of big N. We'll consider any little n bigger than big N. We'll do some simplifying, and we'll take advantage of this assumption that, well, let's take advantage of all of it. So I think I don't know, in the margins or on the board, I want to like do the thing where we try to solve an inequality. So here's the thing we want to mess around with. And I guess that's just going to be f sub n of x is x to the n. F of x, what is f of x in this case? 0. Cool. I need to show that that's small. So let's mess around with that and see what we can do with it. What can we do with that? Everything's positive, so the absolute values don't matter. It doesn't matter if you subtract 0. All right, what can you do with that? I can make little n bigger than big N. And x is less than 1, so raising it to a bigger power makes it littler. Oh, cool. So now there's like a big N instead of a little n. You know what I'm going to do? I'm going to set that equal to epsilon and solve. What do you get when you solve that for epsilon? And maybe there's something that's a little bit dicey here. Let's assume that there exists a logarithmic function that has the properties that logs have. That seem kosher? Yeah. So, let's go for it. So let's consider any x in between 0 and 1. Oh, and let's maybe even take a check. Would that be bad if x were literally equal to 0? Yeah, you can't have 0 in the base of a log. Maybe that's like distant memory knowledge. But let's let big N be log base x of epsilon. We'll consider any little n bigger than big N by simplifying and using all this. Well, I mean, I don't know. Is it actually worth the effort of me writing out the rest of the proof? Should I just be, I'm just going to be quiet for a second. Fill out the rest of the proof, and then maybe we'll, like, say the words. So I guess the next couple lines are just like what's in the margin anyway, right? Nice. So I guess the first step was like the absolute value bar doesn't actually matter. Next, since little n is bigger than big N, which is log base x of epsilon. And maybe I'll stick another thing in there. And since 0 is less than x is less than 1, this is less than x to the big N. Notice like that step does actually, that thing I underlined in green is actually important, right? If x were 5, raising 5 to a bigger number doesn't make it smaller, it makes it bigger. Less than x to the n, which is in fact equal to epsilon. Neato. Yeah.
Point out somewhere in here that x being smaller than 1 is, I mean, it's,
Oh, sure.
we say that it's true, but we don't say that that means that it
Here, 0 less than x is less than 1 is important. For the implication. Yeah. And that's fair enough, right? If there's stuff that seems like hidden, why it's important.
you don't necessarily say that like on that interval it's a decreasing function or something like that.
Oh, for sure, yeah. I.e. x to the n is a decreasing sequence. Which, that's maybe a better way of saying what's right there.
Yeah.
Red light. So maybe instead you could replace that with this. Yeah. Here, 0 less than x less than 1 implies x to the n is a decreasing sequence. So x to the n is less than x to the big N. Yeah. Maybe there's the better way to write it. Yeah. Groovy. So, that looked like a proof of pointwise convergence? Cool. Let's try to uniformize it. So let's try to come up with a version of the same proof where we say we're only going to walk between 0 and c, where c is a number that we'll pick in advance. And try to come up with a choice of big N that doesn't depend on x. Let's try to do it. Yeah, I guess so. Here, either way, we see that for all x in 0, 1, f sub n of x converges to f of x. That does the job. Next, we prove the uniform convergence claim. We'll fix some c between 0 and 1. Let's consider any epsilon bigger than 0. And let's recall the statement of uniform convergence, because it's like a little bit pickier. Remind me what that means. I guess flip to the previous page if you got it. So the idea is just to get big N to not depend on X. Yeah. Yeah, I just read that. And now I want you to tell me what that means. That explains how I know what I was answering.
Epsilon greater than 0, there's this big N such that for all N greater than N, and for all X in U, then F the value F sub N of X minus F of X is less than epsilon.
Nice. So there's what we need to prove. Where here this U isn't, well, it's a specific set. It's 0 to C. My C looks too much like a 0. There. Now it looks like a tiny little K. All right. So there's the thing I need to prove. And the nice thing about logical statements like this is they tell you how the proof should look. They tell you how the proof can look. We'll start by considering any epsilon bigger than 0. Well, so once we have set up, so fix the C, consider any epsilon bigger than 0, and we'll need to come up with a choice of big N that can only depend on epsilon, and I guess also on C. It might depend on C. We'll consider any little n bigger than big N and any x between 0 and C. Then we'll go through a bunch of the same work. We'll try to compute the absolute value of f sub n of x minus f of x. And here we'll use that. Yeah, I'm still on the page. And simplify. So I think that this requiring that x is less than or equal to c is less than 1 successfully eliminates the case that x equals 1. So like, this case-wise stuff doesn't matter. I just need to show it gets close to 0. So let's do that. For this choice of x, what does f sub n of x minus f of x in absolute value simplify to? All right, what next? Well, I'd like to get rid of this dependence on x, yeah. What? Yeah, say what you want to say.
I was saying that's less than 1.
This is true. This is true, but eventually I want to get like a less than epsilon there. So like just less than 1 isn't going to be good enough. I need to show that it's less than something that I can show is also really, really small. Yeah.
I think it's less than x of big N.
That's still true. And this is like a bad writing problem. They are the steps that are involved in that implication. Is that something I could like set equal to epsilon and solve for big N? I could, right? In fact, that's exactly what we did in the previous page, on the previous step of the proof. So that would be like, that would suggest that big N equals log base x of epsilon, right? Yeah.
Can we do something like c to the n, c to the big N?
Yeah. Alright, so this is bad because that depends on x. The whole point of uniform stuff is to avoid this dependence on x. Is that something I could set equal to epsilon and solve for big N in the exact same way? In fact, you'll get the exact same formula except the x is replaced with a c. So let's use that. Let's fix some c in 0, 1. Let's consider any epsilon bigger than 0. We'll let big N be log base c of epsilon. All right, so I guess well, since big N is equal to log base c of epsilon, c to the big N is now just equal to epsilon. And I guess now some of the wads don't line up correctly because some of the stuff in the step above is justified by the sentence below. How do we feel? Does that seem like a proof? Maybe we'll do a quick read through and see if it does everything I need to. So I start by considering any c in between 0 and 1, which is good. That's just part of the statement of this claim. I then consider any epsilon. I come up with a choice of big N. That choice of big N is independent of the choice of x, although it does depend on what c you use, and it depends on epsilon. Consider any little n bigger than big N, any x in the relevant domain. F sub n of x minus 0 is now shown to be less than epsilon. That seems like a proof of uniform convergence. So, maybe here's the thing that this is suggesting. So, pointwise convergence can have a bad point. This behavior at x equals 1 is weird in the limiting function. It's like a discontinuity. If you cut it off before that, you can get uniform convergence. And that uniform convergence seems to preserve the continuity of the limit. Maybe let's do one last thing. In order to really understand what uniform convergence means, let's prove that this sequence of functions does not converge uniformly on the whole interval. And to do that, I think we should write down what we need to prove. So, finally, we prove that S of n does not converge uniformly to f on 0, 1. By negating the definition of uniform convergence, let's see what we have to prove. And I'll put the negated line right here, but maybe off to the side. I got space in the version. Let's negate the definition of uniform convergence slowly. So I'm going to rotate not, and then I'm going to put the definition of uniform convergence. For all epsilon bigger than 0, there exists a big N such that for all little n bigger than big N, for all x in the domain, absolute value of f sub n of x minus f of x is less than epsilon. There's the thing I want to negate. Now that that's written down, is it easy to negate? Yeah, so I just need to show that, well, let's say it though. What do you get when you negate a universal? There exists epsilon greater than 0, such that
For all n, there exists n greater than big N. There exists x in 0 to 1, such that f sub n of x minus f of x is greater than or equal to epsilon.
nice, cool. So, doing that, we must prove that for some, I don't know, I probably don't have enough space in this line for me to write it out in words. There exists an epsilon bigger than 0, such that no matter what big N you choose, there exists a little n bigger than big N, there exists an x in 0, 1, such that f sub n of x minus f of x, well, but what is well, I guess, here's what I need to show. It was totally off screen, but that's okay, you already wrote it down. So that means step one is let epsilon be equal to, and then like I don't get to choose, it just has to be a number. And in order to help choose that number, and maybe even get an idea of how the proof is going to go, here are some like really close zoomed in pictures of this for x to the 100, x to the 200, and x to the 300. Looking at each of those pictures, can you see a point where that graph is not very close to the limiting function? Yeah, the limiting function is 0 except at x equals 1 where it's 1. Do you see a place on this graph where the function is not very close to 0? What input are you looking at? Oh yeah, but 1, 1's no good because f of 1 is 1. I need an input other than 1.
Close to 1.
Yeah, number like close to 1 but not quite 1. And that not quite is allowed to depend on the choice of big N. Ooh, okay, cool. Yeah, so I guess that means like I can get these y values to be as far away from 0 as I want, up to 1. I can't quite get them bigger than 1. I just need a choice of epsilon. So it looks like any epsilon value less than 1 I can walk with. Give me an epsilon that's less than 1.
0.95.
Not what I was thinking. It'll do. I thought you were just going to say half. Write what you want in your notes. I'll stick with the 0.95 just to illustrate the fact that it doesn't really matter. So let's take epsilon to be 0.95. Let's consider any n. And in fact, by looking at these, is it going to matter what little n is? So I just need a little n that's bigger than big N. Give me a little n bigger than big N. You could just say let little n be anything bigger than big N, but this way it's like literally doing the job it wants. It's supposed to be an existential, not a universal. I need to cook up a choice of big X, a choice of X. So we could certainly like set x to the n equal to 0.95 and like do some solving, right? And you'd have to take like the nth root of 0.95. That seems like a weird thing to write. Instead, I'm going to use the fact that we've like built up the fancy tools from calculus, like the intermediate value theorem. Is x to the n a continuous function? Is there an input where x to the n is less than 0.95? What input are you thinking of?
0.
Yeah, I guess you better be thinking of 0, otherwise I'd have to change the notes follow. That's less than epsilon. What's f sub n of 1? 1. That's bigger than epsilon. Because 0.95 was our choice of epsilon. Since f sub n is continuous on 0, 1, we see by the intermediate value theorem that there's some x in between 0 and 1 with f of x equal to epsilon. And just in order to cover my bases, I think the way I stated the IVT, I included the endpoints as the things that x could be, so that I could write more things as less than or equal to's. So I guess I better know that this x isn't equal to 1 because f sub n of 1 is weird. Why is this x not equal to 1? What's f of 1? 1? F sub n of 1, rather, is 1. Is 1 equal to 0.95? No. This x cannot be 1 since f of x equals 0.95, but f of 1 equals 1. Oh, and all that was supposed to go in this blank. That's okay. So, we now have an x in between 0 and 1, excluding 1, which satisfies that f of x is equal to epsilon, or 0.95. Let's expand this out. So use all the information above. What is then f sub n of x minus f of x for this particular choice of x? Let's just plug everything in. What is f sub n of x for this particular choice of x? .95, or whatever you've picked your epsilon to be. What's f of x for this particular choice of x? Well, remember, f of x is the pointwise limit. Cool. Oh, cool. Is that bigger than or equal to epsilon? Yeah, in fact, it's equal to epsilon. Cool. So there exists an epsilon, namely 0.95 is the one that we used. Or maybe you used 1/2, or whatever. So that for any big N, there exists some little n bigger than big N, so that no matter what x you pick, for some n bigger than big N, and some x, absolute value f sub n of x minus f of x is bigger than or equal to epsilon, that negates the definition of uniform convergence. This sequence does not converge uniformly. Cool. So, I guess we haven't really done anything fancy with uniform convergence. We've just shown some examples. Yeah, there's enough time to do this gradually. But this example should illustrate something. So here's something that you would want to happen. So here, oh, God damn it. Question 8.1.5. If f sub n is continuous for all n, so we have a sequence of functions, each one of those functions is continuous, and f is the pointwise limit of this sequence of functions, does it follow that this limiting function has to be continuous? I'm going to count down a few more seconds, and I'm just going to ask a show of hands for yes or no, this does or does not follow. Folks, what this does follow? Folks, what this does not follow? 4. I guess that would mean the remaining 4 are maybes. Those of you who said no, why not?
Limit points. That means I feel like it doesn't consider the point is actually in your function or something like that. It feels like somehow a uniform limit would help that. It's mostly just a guess. I'm trying to use my intuition.
Well, how about this? Like, we have an example already. The sequence of functions we just proved this proposition about, x to the n, is for every n, is that function continuous? Does it converge pointwise to a limit? Is that limiting function continuous? No, it's got this like jump at 1. So that sequence of functions is an explicit counterexample to this one. So that's one that like you could answer definitively. Uniform limits. So if f sub n is continuous for every natural number n, and f is the uniform limit of the sequence of functions f sub n, does it follow that f is continuous? I'm going you ask the same intuitive question, yes, no, maybe. Anyone want to say yes? Cool. Anyone want to say no? Anyone want to say maybe? I feel like that does in total 8. Anyway, yeah, we certainly haven't proven it, but the whole point of uniform convergence is the following. If you take a sequence of continuous functions that converges uniformly, the uniform limit is continuous. And, well, a powerful thing you can do with that is you can use that to cook up really weird functions. You can find some sequence of continuous functions that converge uniformly, but have some bad behavior that builds up. And one thing I'll recommend you do when you get like internet access and it's convenient, look up the Weierstrass monster function. It's a function that's perfectly continuous. It's a nice function, but at no point does it have a derivative. It's all corners when you look at the graph, whatever that means. So you can come up with really nasty functions using this fact by approximating, but they're still continuous. Limits. Let's suppose the following. So still, suppose that you have a sequence of functions, f sub n of x, that for each n, the limit as x approaches c to f of f sub n of x is equal to L sub n. Let's suppose also that the limit as n goes to infinity of L sub n is L. Then does it follow that the limit as x approaches c of the limiting function is L? Said another way, can you reverse the order of those limits? And maybe we'll mess around with exactly the same example. Let's take the limit as n goes to infinity of the limit as x goes to 1 of x to the n, as opposed to the limit x goes to 1 of the limit as n goes to infinity of x to the n. Let's try to compute those two limits. And I think we'll do it from like the inside out. If you fix n, what's the limit as x goes to infinity of x to the n? 1. Awesome. So this is the limit as n goes to infinity of 1. What's that limit? So if I want to take the limit as x goes to 1, let's even put like a little minus there. We haven't used that notation in the class, but in the context, I only care about numbers between 0 and 1. That's like the limit from the left. To compute this limit, when you want to compute the limit as x goes to 1, you don't actually care about what happens when x equals 1. In fact, you only care about what happens when x is less than 1. If you take an x strictly less than 1, then what's the limit as n goes to infinity of x to the n? 0. Right, like if x is like 0.95, you raise that to bigger and bigger powers, that goes to 0. So this becomes the limit as x goes to 1 from below of 0. And what is that? Cool. Can you always reverse the order of limits like that? And I guess like I ruined the like whole thing there. The other point of uniform convergence is you can reverse the order of limits. So as soon as you have uniform convergence, you can switch the order of limits, which is something that's like super obvious that you want to do. And if you read like the old like origins of calculus, like the works of Newton and stuff, like they just assume you can. A lot of the old works like that build up calculus and analysis just assume that a lot of things are true, just work out fine. And then the next like century is just checking those details and seeing that they're actually wrong and that you need some extra hypotheses. Cool. So I've got, I think, a moment. Let's take a tour of what's left in this packet. So in the next unit, we are going to prove those claims that uniform convergence is good. Uniform convergence resolves continuity. And then after we do that, we are going to prove that if you have uniform convergence, then you can do this switch the order of limits thing. And like, that theorem is obvious enough that like, you don't want to just like read it right now. That's what it says. It says you can switch the order of the limits. We'll do some other things with that. Well, let's remember this. If you have a sequence of numbers, and it's too hard to check whether it converges because you like don't have a candidate to be the limit, but you just check if the thing's Cauchy. Or maybe you check if it's monotone, but probably you check if it's Cauchy. Same thing with sequence of functions. There's a Cauchy criterion for pointwise convergence, and it's the obvious one. Like if I just ask you what should it mean for the sequence to be pointwise Cauchy, you'll write it down automatically. And then if you do that, I'll ask, well, what if you want this big N to not depend on the choice of x? Make that change, and you have the uniform Cauchy criterion. And Cauchy's theorem still holds in this end. Pointwise convergent if and only if pointwise Cauchy. Uniformly convergent if and only if uniformly Cauchy. And the last thing that we'll do is we are going to talk about power series. And I guess you can tell based on this setup what we'll do. In order to get continuity of a power series, you need uniform convergence. How do you get uniform convergence? You get uniform Cauchiness. So we'll show that the sequence of functions that approximate a power series converge uniformly, and then we'll be done. And that's the last thing that will happen in this class. Cool. And I think at no point will I ever be good at like actually cutting off the end of a class. Like, I'm past time, but I'm bad at saying goodbye.